So a big portion of the exam is knowing which analysis to do, right? So if you only have quantitative information, 2 quantitative variables, you know you're dealing either with correlation or regression. What's the difference between correlation and regression? Correlation, you're just saying these 2 things are related. They're related in some meaningful capacity. Quantitative information. A regression takes it a step further and says you're predicting one variable from the other. It chooses one as the likely cause and the other as the likely effect. It says use A to predict B, use X to predict Y. Does that make sense? And then if you only have categorical information, people in groups, and how many people were in those groups, so the answers that people would have provided are categorical. For example, are you from LA or not? Do you volunteer or not? What's your favorite TV show? If you only have categorical information, it has to be a chi-square. And then you just ask yourself the question, do I have 1 categorical variable? Goodness and fit test. Do I have 2 categorical variables? Test of independence. So there are several, there's like dozens. I give you dozens of different research scenarios in that PowerPoint. Go through them, try to go through them without the answers and see if you can decode them. What analysis should I do here? 1 sample z-test, 1 sample t-test. And really, the 1 sample z-test, you're not going to be able to tell the difference, right? Unless I explicitly tell you about variance, right? Based on the scenario, you'll probably go, well, I only have 1 sample here that's measured quantitatively. It's got to be a z-test or a t-test. And then on the exam, I might then tell you about population variance information or not, right? And so if you see that there's 2 groups, ooh, I have 2 groups here, measured quantitatively, I guess this must be an independent samples t-test or a paired samples. What's the difference? Are these 2 samples meaningfully related? Or they know each other, right? And then if you have only quantitative information, it either has to be a correlation or a regression. If you have only categorical information, it has to be a chi-square. Does that make sense? Like 20% of your test is just that. So make sure you can do that. It must be super important. It may be that essentially the whole point of this class is knowing what analysis to do. Because most of you guys calculate beautifully. Most of you calculate beautifully. The point of this class is to be able to interpret the calculations. Does that make sense? All right. So there'll be a bunch of review material from the previous exam. So hopefully you'll do really well in those previous. It's just dark with the green lights on, so I'm sure it's fine. All right. But then there'll be a bunch of new material on Anova, correlation, regression, and chi-square. So half the exam is covering that new material. And so tell me about why Anova. Why do we have to do Anova? Anova was a pain, right? Why do we have to do Anova? Why can't we just do a bunch of t-tests?
So it increases our chances of type 1 error. That's
right. Doing a bunch of t-tests increases our likelihood that at least once we will commit a type 1 error. Because alpha is our likelihood of committing a type 1 error, right? Of rejecting the null hypothesis, even when the null hypothesis is true. Remember that? That's what a type 1 error is. We've rejected the null hypothesis. We've said, ooh, cool things in the world are here, right? Awesome. There's an effect. People are different. Right? That's the idea behind the null. And so if we reject the null, we say that there's a real effect, but a type 1 error is we're wrong. That in reality the null is true. And alpha is our likelihood of committing that type 1 error. But every time you do a new test, it becomes an or question. What's the likelihood of a type 1 error here? Or here? Or here? Or here? And that's the additive rule, right? So you have to add up all those alphas, and so you have an increased likelihood of committing a type 1 error at least once. And so the Anova allows us to do one test that gets rid of that problem. And so if you reject the null hypothesis in an Anova, what does that tell you?
That they're not equal.
Yeah, that among these averages of at least 3, you could do an Anova with 2, but why would you? Why would you bother, right? The math does not stop you from doing it with 2. It's just you wouldn't, right? So if you have if you reject the null, it says among these averages, at least 2 of them are different from one another. Not at least one of them is different, because that would suggest one of them is different from all the others. But one pair is different from each other. One pair is different from each other. Does that make sense? So that's the alternative. And so previously, all of our analyses before Anova had this basic model. We had some effect, one average minus another average, over standard error, right? And Anova is just an extension of that. It's a mathematical extension of the independent samples t-test. So what is our new basic form? Effect over what? Is it standard error now? No, it's what? So this is the effect variance. What is this variance on the bottom? It's effect versus what? Error. That's right. We calculate the variance due to the effect of our categorical variable versus the variance due to error, which is not that anyone did anything wrong, just all the other variance of the things we're not studying right now. We call it error. So effect over error is the basic function of everything we've done all semester. That's even true of chi-square. It's some effect of the variables you're studying versus error. Either standard error or error variance or expected frequencies. It's always effect over error. This class is all about ratios. Looking at the effect, the signal versus the noise versus the error. And so Anova is the most similar to what other test?
T-test.
Which one? The one Anova we learned in here. Because we only learned one type of Anova in here.
The one with the different t-test.
So which one would that be? Two sample. Which type of two sample? Did we do any repeated measure Anovas in here?
No.
No. So the only Anova we did in here is what is similar to which test?
Independent.
The independent samples t-test. So what are the assumptions of Anova? Which test are they exactly the same as? The independent samples t-test. So what are those assumptions again? Who remembers?
Normality.
Normality. We assume that the populations, not the samples, but the populations, we assume that the populations are normally distributed. That's right. We assume the populations have homogeneity of variance, that the variances are the same. And we assume
they don't affect
independence of observations, that all the people do not impact each other in any way. So if you get a statistically significant F statistic, meaning your P is less than alpha, meaning you've rejected the null hypothesis, and you've determined that among these averages things are different, what then? What do you have to do? Can you go, oh great, groups are different, and go home?
No.
What do you have to do?
The LSD thing or the other one?
Well, yeah, you have to do what's called a follow-up t-test. And the equation for a follow-up t-test is always the same. We take the average of one particular group, subtract it from the average of another particular group, and divide it by standard error. This will give us our t-test, or the degrees of freedom, or n minus g. So you take your mean square within, you multiply it by 1 over n plus 1 over n. And we only dealt in a world where sample sizes were equal. So n is the same number in our world. And so is this equation any different for any of the follow-up t-tests? No, it's always the same. How you calculate the t-test is always the same. So what's different between a Bone-Ferroni, a Tukey's HSD, a Chaffee, or a Fisher's LSD approach? What changes? Why are there different types of follow-up t-tests? Why do they get different names? Who remembers?
Alpha is different.
Yeah, so you're changing your critical value, right? Bone-Ferroni takes the approach of changing alpha directly, right? Fisher's LSD, what approach does that take? Pardon?
Just set at 0.05.
Yeah, it doesn't change a darn thing. It says calculate t this way, but don't change the alpha, don't change the critical value, just use n minus g degrees of freedom. So you have more degrees of freedom, actually, than you would if you were just doing a t-test directly. Right, so you're using this many degrees of freedom, you're using mean square within as opposed to pool variance, and other than that, nothing changes. Use alpha 0.05, look up the appropriate critical value. So is it hard or easy to reject the null in a Fisher's LSD compared to the others? Easier. It's a more liberal approach. It's easier to reject the null. Bone-Ferroni, it takes what approach? It changes alpha, right? What's it do to alpha?
Maybe 0.01.
Well, it depends on how many tests you're doing, right? So a Bonferroni says take alpha 0.05, because that's typically what you do start with, right? And divide it by the number of analyses you're doing. So if you're doing 3 analyses, it does 0.016. But if you're doing 4 analyses, it's smaller. If you're doing 5 analyses, it's 0.01. If you're doing 6 analyses, it's even less than 0.01. If you're doing 7 analyses, if you're doing 10 analyses, it's 0.0001. So alpha gets very, very small the more analyses you're doing. So is it easy or hard to reject the null hypothesis for the Bonferroni approach? Very difficult. It's an incredibly conservative approach. And it's typically only done when you have very few t-tests and very strong effects. Bonferroni. And so then the one in the middle that I taught you was Tukey's HSD, which actually tries to derive the appropriate critical value. And it's somewhere in the middle, right? All right, so let's talk about what you might be asked to calculate for Anova. Follow-up t-test, totally fair game. I might ask you to calculate one of them. What about the Anova itself? So calculating Anova by hand takes forever, doesn't it? It takes a really long time to calculate Anova by hand. And so the likelihood I'm going to ask you to calculate an Anova by hand is nil. But it doesn't mean you don't have to know the equations for an Anova. So here is the equation for the sums of squares between. So I might ask you things in the multiple choice section that look like this. So tell me the first step in calculating a sums of squares between. I'm not actually making you calculate anything, right? I'm just asking you, when you're calculating a sums of squares between, what's the first thing you do? Kind of like on one of your exams, I asked you the first step in calculating a paired samples t-test. Same idea. So what are you going to do? When you're calculating sums of squares between, what's your first mathematical step? Right, you take the individual subgroup averages, all of them, and subtract the grand mean. Now, I'm not going to make you calculate sums of squares for a data set, but you certainly need to know the mechanics of this equation. And I might ask you, in the sums of squares, why is squaring such an important step? Just like I asked you in the first exam, you'll say, well, because otherwise these deviation scores will sum to 0, because they will. Those sorts of things. So knowing these equations is important. Or I might ask you, what's the first step in calculating a sums of squares within? And what would you tell me?
Subtracting the individuals from the group average.
Right. Take each individual person's score and subtract the subgroup average from it. So again, I'm not going to make you calculate these by hand. You do need to know these equations. What I probably will have you do is something more like this. I would ask you to calculate the F. With this information, you should be able to calculate the F statistic, and if I provide you with a critical value, interpret the F statistic. This is much more likely for me to see in your future. Asking you questions about the sums of squares, what is the mathematical operations of the sums of squares, but then having you calculate and complete a table that looks like this, where I give you the sample size, I tell you how many groups there are, and you have to fill in and complete this table. Could you do that? Well, then these would be 5 points that are lost to you.
How many?
Or maybe more. I don't know. I haven't finalized the final exam yet.
How many written questions?
There are 50 points of written. 25 of them are old, 25 of them are new.
What do you mean 25 are old?
Meaning they're the exact same items you've seen before. So I might ask you to wax philosophical about the central limit theorem again. I might ask you to explain to me why we have to do n-1 when we're dealing with a sample when calculating the variance again. I might ask you to calculate a t-test again.
Oh, and then there's 25 points of like these.
This stuff.
So like a couple questions, like 3 or 4.
So yes, so something like this. Maybe calculate your last lab assignment, the correlation and regression one, is excellent preparation for a big part of the final exam.
Okay.
Just like your homework. But something like this as well, right? So what is sums of squares error? It's 100. Why? Because sums of squares effect plus sums of squares error equals sums of squares total, right?
Yeah.
All right. Well, what are my degrees of freedom? I don't remember.
7, 2, and 9.
Right. Because degrees of freedom for the effect is n minus g. Right? So what is no, 97. Degrees of freedom for the error is n minus g. And knowing these equations can help you too, right? Because if you're thinking about it, well, what is error? Well, error is each person minus the average, right? Well, people is n, right? The averages I have are 3. So the degrees of freedom for the within is the n minus 3. So what are the degrees of freedom between? Well, that's g minus 1. Because look here, how many averages do I have? 3. Subtract 1 grand mean from it. So again, knowing these equations can help you remember which is which. And so here I have g is 3, so 3 minus 1 is, so what is my sums of squares total? 99. Because 2 plus 97 is 99, but also n minus 1. I love when math does that. Makes me all excited. It's together like a puzzle. So now how do I get mean square effect? It's 200 divided by 2, right? Is it being 100? How do I get the error? I do 100 minus 97. It's 1 point something, 1.01 or something like that. 0.3? Now you don't actually calculate this because the mean square total is just the variance. It's the total variance for the study. So you don't actually ever put anything here, typically speaking. How do I get my F? 100 divided by 1.03. Just under 100. 97, 98.
97.19.
So that is my F. And so if I told you that the critical value was something like 5.01, which it's not, would you retain or reject the null hypothesis? You reject it all day, every day. You would say, this factor clearly matters. Right? You would say, clearly, whatever categorical variable that you had where there were 3 groups matters. It changed the quantitative variable in some way. And then I may or may not ask you to do a follow-up t-test comparing 2 of the groups. I'll tell you which groups to compare if I'm going to have you do that. And then I may or may not ask you, how much does the category matter? Do you remember the effect size for an Anova? Something called eta squared. Sums of squares between over sums of squares total. So in this case, what's sums of squares between? 2 over 300, 0.67. How would I interpret that? That would mean that the proportion in the quantitative variable that can be explained by the factor is 0.67. So let's say this is the TV groups. Because that was 3 groups, right? A little TV, a lot of TV, or no TV at all. And I was measuring aggression. This would mean that 67% of a child's aggression can be explained by how much TV they watch. By which group they were in. This is eta squared. And that are the kinds of things that you would have to calculate for an Anova. Any other concept stuff for Anova? Nope, that's it. All right, so know that stuff for Anova. Is that confusing at all? Good. All right, right, so then we did correlation and regression. Would you like to work through an example or just talk about it?
Work.
So with a correlation, you have two variables, both are quantitative. How much sleep did you get last night?
2 hours.
9 hours?
Damn.
How much coffee do you? How much coffee you drink today?
1 cup.
How much coffee you drink today?
0.
0. How do you function?
I don't know.
All right. How much sleep did you get last night?
7 hours.
Did you drink caffeine? All right. How much did you sleep last night?
I think 9.
I don't have time to
Did you drink coffee?
1 cup.
Ah, my sleepers and my coffee drinkers, man. That's okay. Let's do it. So first thing I have to do to calculate a correlation is I should probably start by calculating the two standard deviations, right? Because the best equation for calculating the correlation takes the covariance and multiplies it by the two standard deviations. You don't have to do it this way. You can use the z-score equation, but why would you? Why would you? I wouldn't. Right? That's me. So we go ahead and we need to calculate the average. So the average amount of sleep in this class is 18, 20, 27 divided by 4. What is 27 divided by 4?
Let's make it 28.
Do you want to just make it 28?
Yeah.
Maybe you'll take a nap today.
Yeah.
So what's the average? What is it? 7? Yeah, because I can't do math right now. So the average is 7. So to calculate the standard deviation, first I have to get the deviation scores, right?
Mm-hmm.
I'm going to go ahead and do that with this over here too. So my average over here is...
Let's make it 4.
No, I think the average is a half, isn't it? That's not too bad. So I say that x bar is 7, and then 2 divided by 4 is a half, so y bar equals 0.5. Yeah?
Mm-hmm.
All right. So then now I like to do it this way, where I do all the steps at the same time for each variable, because then it helps me keep track. But if you want to calculate the standard deviation over here, and then calculate it again over here, be my guest. I don't care. I'll never know. So now I have to get the deviation scores. I'm going to go ahead and switch. No, I don't have other colors. Oh well. I'll just have to make sure not to make mistakes. So now I get the deviation scores. Equals -4. Equals
2.
+2. Equals 0. Equals +2. And these are the ones that I'm going to need later on for my covariance, right? So I might just give these their own special label. Remind myself these are the deviation scores. And so I do the same thing over here. -0.5 is the deviation scores. +0.5, -0.5, +0.5. And so to get my standard deviation, though, I have to square these, right? Yes. So my next step in calculating a standard deviation, remember then that was hard? Now this is where we start, right? So now my next step in calculating a standard deviation is to add all these up, right? So I end up with 0.25, 0.25, 0.25, 0.25, so I end up with the sum of squares for y is 1, right? Now if I want to turn this into the variance, I divide this by n minus 1. What's my n here? 4. So the variance for y is 0.34. No, 0.33. Round down. Okay. So then I do the same thing over here. I get 16 plus 4 is 20, plus 20, 24 divided by 4 is 6.
24 divided by 3.
Wait. 20.
24 divided by 3.
Divided
Oh, yeah, divided by 3.
What?
So 8. And minus 1.
Got it.
So then I end up with the variance then is, the variance for x is 8. Made it bigger on purpose. All right, so now to get the standard deviations, I take the square roots of these, right? So what's the square root of 8?
2.83.
What is it?
2.83.
And the square root of 0.33 is?
0.57.
Cool. So, do I have these two standard deviations now? But I haven't gotten the covariances yet, right? Darn. I'm going to need to multiply these deviation scores for person 1, person 2, person 3, and person 4 by these deviation scores, right? So I might make myself a column over here called x times y to remind myself about what I'm doing. There might be a chart and with columns on your final exam to help you organize. Looks like I'm doing right now. So I take negative 4 and I multiply it by 1/4. I end up with negative 1, right? Yeah? Is that right? So 4, is that right? It's okay. Oh, wait, am I multiplying the wrong number? See, I'm multiplying the wrong number again. So negative 4 by negative 0.5 ends up being a positive 2. Don't be me on your final exam. Make sure you're multiplying the right thing by the right thing. Oh, man. Okay, so I end up with positive 2 by positive 5, right? 0.5. So I end up with positive 1. Ooh. Okay, so then I end up with 0 times, it doesn't matter because it's 0. And then I end up with positive 2, is that right? By positive 0.25?
No.
Oh, no, by positive 0.5. Yes. That's why I like to switch colors, but I forgot my other pens. Okay, so that would be positive 1. So to get the covariance, to refresh your memory, you get the deviation scores for x, the deviation scores for y, cross-multiply them. Have we done that?
Yes.
Yes. Now I need to add them up and divide by n minus 1. This is the average cross product.
So 5 over
So we end up with 5 over
3.
3. So let's,
Isn't it 4?
4, yeah.
4, yeah, 2 plus 1 plus 1, 4. So I end up with, what is it, 1 1/3? 1 1/4?
Yeah. 1.33.
1.33, 1 1/3. So this is the covariance. Notice how it's positive? Because there was this sort of positive relationship. My coffee drinkers were my sleepers in my 4-person data set. Just happened to be the way it fell out. I drank coffee today and I got 7 hours last night. 7 hours. All right, so this is the covariance, right? It's unstandardized. Meaning, do I know how to interpret 1.33? No, you know it's positive. There's a positive relationship here, as we see. There's certainly a positive relationship, but we need to turn it into the correlation. And so to turn it into the correlation, this is my equation over here, right? So I take my 1.33 and divide it by the standard deviation for x times the standard deviation for y, which is 0.57. Start on the bottom, 2.83 times 0.57, what's that?
1.61.
1.3 divided by 1.61 is
0.82.
0.82. Well, that is a very strong correlation, isn't it? Now, I could do a null hypothesis significance test on this 0.82. I could. But this is just a descriptive statistic, right? It's a descriptive statistic based on these 4 people. That's it. A descriptive statistic based on these 4 people. And so, if I did a null hypothesis significance test, this would tell me whether or not in the population I could reasonably use these 4 people to decide that the real relationship between coffee and sleep is statistically significantly different from 0. You have to understand that concept for the final exam, but you're not going to have to calculate that at all. Just understand that a correlation is simply a descriptive statistic that then you could do a null hypothesis significance test on. Does that make sense? Is this 0.82 statistically significantly different from 0? All right, so now I have this correlation. And let's say that I've decided that this correlation is in fact statistically significantly different from 0. With 4 people, I would probably never conclude that because null hypothesis significance testing, t-tests, are driven by sample size, and I only have 4 people, right? But whatever. Let's say I can determine that this correlation is in fact statistically significant. I then might be able to make a regression equation, right? Create a prediction equation based on this correlation where I predict the number of hours of sleep you get, predict the number of coffees you drink based on the amount of sleep that you get. Does that make sense? And to do that, I calculate 2 things. I have to calculate a slope for a line, and I have to calculate the Y-intercept for the line. And there's a couple of ways to calculate the slope, but I think that the one I like is the covariance divided by the variance of x. I really like that one a lot. And then to get the Y-intercept, there's another one you can do with the correlation though, right? Is that the one you like? Anyone want to refresh their memories on that one? Yeah, it's R multiplied by the standard deviation, not the variance, but the standard deviation of y over the standard deviation for x. Pretty darn sure. But that involves 3 numbers. This is 2 numbers. You've already calculated.
Yeah, the correlation.
All right, so then we have, so what was the covariance again? What did we say that covariance was? 1.33. What was the variance of x? Well, I find my x variable. My variance was 8, not the standard deviation, but the variance. Right? So what is my slope?
0.167.
0.16.
0.167. You put 1 before the point.
0.167.
There we go. All right, so you can also interpret this slope. And knowing how to interpret a slope will appear in your future. So how you interpret this slope is you say, okay, for every one point increase in x, there will be a slope unit change in y. So what that means in terms of practical application is that for every 1 more hour of sleep you get, I imagine you drink 0.167 more cups of coffee. That's what that means.
So is that the unit change in x?
That's right. For 1 unit change in x,
Oh, it's the same thing.
so for a 1 unit change in x, there will be a slope unit change in y. If the ratio it's like a ratio of 1 to slope.
Mm-hmm.
When x changes by 1, y changes by a slope. Does that make sense? Because the slope is rise over run. So as you move over on x1, y changes by a slope, by the slopiness, by the steepness of that line. Because that is what regression is, right? The correlation of 0.82 is the standardized linear association between the variables. Must be a super important thing, or I wouldn't keep saying it slow like that. The correlation is the standardized linear association between the variables. It's a descriptive statistic that then you can use to create a regression equation where you make some predictions. Where the slope, if you can determine there is some linear relationship here, the slope tells you if as you go up 1 on x, what on average can you expect the change to be on y? So it is also descriptive and useful in terms of description. Regression, you can use it to describe things, right? For 1 more hour of sleep, people are drinking less than a 5th more cup of coffee on average for these 4 people. Does that make sense? You can also get the Y-intercept, which you can interpret. The Y-intercept is the average of y, 0.5, minus the slope, 0.167, multiplied by the average for x, which in this case was 7. So So what's 0.167 times 7?
1.169.
What is it?
1.169.
6.
169.
1.16.
9. Yeah.
Awesome. And I can't hear today. All right, so then we have 0.5 minus 1.167. So what is that?
Negative 0.669.
Negative point what?
0.669. Point, yeah.
All right, so this means, and you can interpret this, that if someone tells me they slept not at all, 0, that means they somehow drank negative cups of coffee. Now, this is technically extrapolating. Why? Because 0 is not in the original range of x, right? So do you see how this ends up with a nonsense answer? Because people don't drink 0 hours. People don't sleep 0 hours, at least not in this data set. And so I have a prediction equation where this is my y-intercept. It's the value of y when x is 0. If you tell me you sleep no hours of night, no hours, 0, no hours of sleep, I would predict you drink negative cups of coffee. Half a negative cup of coffee. Does that make sense?
But why 0? Because we use 7. Didn't we use 7 for the...
No, 7 is the average. This is the y-intercept. This is the y-intercept. So if I plugged in 0 into the equation for x, then it would spit out this number.
Oh, okay.
Does that make sense? Yeah. So this is the y-intercept. It's the value of y when x is 0. Does that make sense? The value of y when x is 0. And this is technically extrapolation, right? Which is why you get this nonsense answer.
Why?
Well, can you drink negative cups of coffee?
No.
Did anyone report doing 0?
No.
Did anyone report sleeping 0? And so here we have our prediction, the value of y when x is 0. So because now I have my prediction equation, right? My prediction equation now looks like this.
Oh.
Y hat, not y, but y hat. I have negative 0.669 plus my slope, which is, where's my slope? 0.167 times x. If I put 0 in for x, what's my prediction? The y-intercept. And because 0 isn't in my original data set, you see how I end up with a ridiculous answer?
Okay.
Does that make sense? You get the y-intercept, which then this will be the answer when you put in 0. Does that make sense? Yeah, the math is like a puzzle.
If we put in 5, it would be fine.
Yeah, not extrapolation.
It just has to be
Within the range.
Picture the number. Where do you get the number from? Like,
You mean x?
Yeah.
Put in any number you feel like.
She tells us.
Oh, you tell us.
Yeah, like on the homework, I told you do x, 6, and 5 is the ones they
okay.
give you on the homework, right? You can put in any number you want. Just be careful not to put in a number that's outside of the original range.
Okay, so let's say you gave us 0, and it didn't work, and we say it doesn't work because 0 is not.
Well, it works. It's just the prediction that you get can be erroneous.
But don't we just say it's extrapolating because it's on?
Well, if I ask you about extrapolation, then talk about extrapolation.
Oh, okay. Okay.
If I don't ask about it, you don't have to talk about it. Okay. So now I have my prediction equation, right?
Yeah.
We need to be able to interpret both the slope and the y-intercept. So correlations are interpretable, right? Correlations are interpretable because they can only range from what to what?
0 to 1.
Yeah, positive 1 to negative 1. They're bounded mathematically by positive 1 and negative 1. You can't have a correlation bigger than 1 or less than negative 1. So what is the nature of the sign? If I say there's a positive relationship because it's a positive correlation, what does that mean about the relationship between the two variables?
They're positive, direct.
Right, so let's say there's a positive, is there a positive relationship here between caffeine intake and sleep? Yes, there is in this data set. I calculated a correlation of 0.82, positive 0.82. What does that mean about these 4 people? That the people who are sleeping more are what? Drinking more coffee. The people sleeping less are doing what? Drinking less coffee. So let's say I had a more reasonable data set with, maybe a random sample from the population, and I had a negative relationship between sleep and coffee. What would that mean? The people sleeping more would be drinking less coffee. The people sleeping less would be drinking more coffee. So know the difference between positive and negative relationships. So what kind of relationship, know the problems with correlation and regression. Would you ever do a correlation on something called a nonlinear effect?
No.
Where you might have like a U-shaped curve or an inverted U-shaped curve. You'd never do a correlation or a regression on that because it wouldn't make sense. I would know the assumptions of regression, right? Know those pretty well. Multivariate normality of the residuals, homoscedasticity equals spread around the line, and independence of observations. Know what those are? Does correlation imply causation?
That rhymes.
I know. Well, it's an oscillance. Let's see. Doesn't matter. So correlation does not imply causation. But what does it mean? If I tell you that people who tend to do better on exams are the people who, tend to study more, what does that tell you? Can you tell me for sure that studying more causes higher exam grades? No, it's a hint, but you can't say that for sure. What can you safely say? Yeah, well, it may not directly causally factor in, but you can say people who tend to study more tend to be what? Tend to get the better grades. That's all you can say. Higher scores on one happen to go with higher scores on the other. It may or may not be causal. That is a separate question. So we would say that correlation measures the spread of the dots, right? Start with a scatter plot. Start with a scatter plot. And so a correlation conceptually measures the linear association between these two variables, the standardized linear association between the variables. And essentially it goes, what is a number that represents how spread out these dots are? The closer this number is to positive 1 or negative 1, the more these dots approximate a straight line. So it measures the spread of the dots. But a regression takes it a step further and finds the best fit line between these dots, right? Finds the one line equation, y hat equals a plus bx, where you calculate this and this, finds the one line that best represents these dots. So correlation is the spread around the line, where regression is the line itself, right? And so technically, although we don't actually do this, the regression line, when we calculate the slope based on the correlation, and we calculate the Y-intercept based on the slope and the averages, this line minimizes what? What does this line minimize mathematically?
The distance each dot has to the line.
That's right. And technically, if you wanted to do a function, for those who remember what functions are, functions of the residuals, technically this best fit line, this unique line we calculate, minimizes the squared distances, the squared residuals, because that's what's left over. Because this is people's actual y-scores, right? And we want to minimize the difference between the y-hats and the y's. And technically, mathematically, you're minimizing those square distances. This is called a least squares criteria. Find the one line that minimizes mathematically the squared residuals. So then we talked about chi-square, right? Two different types of chi-squares that we went over. There are lots of others, but we're just covering two of the basic ones. Because a chi-square deals with is useful when you only have categorical information. It's one of the ways it can be useful. And so ties are good as a fit test. You only have one categorical variable where you compare what you observe to what you expect. That's your effect. Over what you'd simply expect if the null hypothesis was true. Think of that as like error. Add all those up for each one of your categories, and that will give you a chi-square, goodness of fit test. So let's do an example. Joan, dogs or cats? Joan, dogs or cats?
Dog.
Dogs or cats?
Both.
Dogs or cats? Okay, who owns just dogs? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, who owns just cats? One person? That's okay. Who owns both? Wasn't there someone else who said both? No, I own both. And who owns none? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's say my null hypothesis is that all these categories are equal. That there really isn't a preference about pets. There are just the same number of people who own dogs, as own cats, as own both, as own none. Does that make sense? That will be my null hypothesis. So how many people are there in class today? 10, 12 plus 14. So 26? That's 26. 26 people. So let's just assume that there are 2 fewer people here. So if the null hypothesis is true, how many people should be in each category? So 10 plus 24, 24? 6 in each category, right? If the null hypothesis is true, and this categorization that I made doesn't matter, the same number of people are in each category, this is what I would expect to see in that null hypothesis. I don't have to do this kind of null hypothesis significance test. I could compare it to a population. I wonder if my statistics class is different from some population, right? I could put all the dogs in one category, and that's what I'd expect in my null. I could put all the cats in one category, and you know what I mean? You don't have to do it this way. This is just one of the null hypotheses you could test, is that all the frequencies are exactly equal. Does that make sense? And you determine how well this null hypothesis model matches what you actually observe. So let's find out. So I start with my first category. What I observe is 9 minus what I'd expect is 6, divided by what I'd expect. So I end up with 3 squared over 6. I end up with 9 over 6. Ends up being 1 something. 1 1/2? Can't do basic. 1 1/2. I'll do that for the first cell. I'll do that for the second cell. What did I observe? 1 minus 6 over 6.
4.1.
So I end up with 1 minus 6 is negative 5. Is that right? Over 6. I square that. It's called a chi-square. I end up with 25 over 6. And what is that?
1.7. I mean 4.17.
So notice how this is a bigger number, which is going to now feed into my chi-square because this was a bigger deviation from what I'd expect. Do you see that? So I have to do it for the next category. 2 minus 6 over squared over 6. I end up with negative 4 over 6. Squared is 16 over 6, which is what?
2.67.
2.67. Do it for my last category. 12 minus 6 squared,
We're gonna have to do one of these on the test.
maybe, over 6 equals negative 6 squared over 6 equals 36 over 6, so 6. Yeah? Now I just add these up. Add these up.
14.34.
What is it?
14.34.
14.34, so my chi-square is 14.34. Now I have to compare this to a critical value, right? Now the critical value for a chi-square goodness of fit test is going to be the number of categories minus 1, right? So what's that?
You're so annoying.
3 in this case, right? So my critical value for 3 degrees of freedom is going to be some number, probably around 7 something. So let's say it's 7.1. Would I retain or reject the null hypothesis? Reject. Clearly, we do not have an even split in this class. People are far more likely to own no pets or dogs than to own cats or both. Clearly, we are all cat haters in here. Does that make sense? Yeah? Now, the other kind of test you can do with a chi-square is when you have more than one categorical variable and you want to know if the categories are meaningfully related. So let's do one more live data collection.
Really?
Yes, really. I know those from outside. Almost from outside. So I'm going to ask everybody their gender, and you don't have to tell me your actual gender. Just pick one. Pick whichever gender you feel like you are today. I don't care which you pick. Right? I know, right? And I'm going to also ask you, males, females, and again, this is on a spectrum, whatever, but you're going to pick one for purposes of today. And I'm going to choose the beach or the mountains as a vacation spot. Don't worry, I'm paying, right? But you can only pick one. You can only pick one place to go, because I'm curious if self-identified gender it has any relationship to where you might choose to go to the right. So if you would like to be considered a male today and you would like to go to the beach, raise your hand. 1, 2, 3, 4, 5. Okay. If you would like to be considered a female today and would like to go to the beach, raise your hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so if you would like to be considered a male today but would prefer to go to the mountains, raise your hands. 1, 2. If you'd like to be considered female today and would like to go to the mountains, raise your hands. 1, 2, 3, 4. Okay. Now clearly, people are much more likely to want to go to the beach, right? So even if gender and where you want to go on vacation have nothing to do with one another, going to the beach should be my biggest category, right? I should see that. Because let's look at the marginal frequencies here, 18. And look at the marginal frequencies here, 6. And let's compare males to females. There are clearly more self-identified females in this room, right? Period. So what should be my biggest category? This one. Even if gender and where you want to go on vacation have nothing to do with one another, this should be my biggest category, right? So I can't just assume an equal spread. I have to actually calculate my expected frequencies. Does that make sense? So that's what I have to do. So what was my total N?
24.
What is it?
24.
24 again? Well, that's nice. Thank you, 2 people, for not voting. Yeah, whatever. Okay, so I actually have to calculate my expected frequencies before I calculate my chi-square. This is what I observed. And now I need to calculate what I'd expect if gender and where you want to go on vacation have nothing to do with one another, right? And how I do that is by looking in the marginal frequencies. So to calculate the expected value for this cell, I take 18 times 7, and I divide it by the total N, 24. For this cell, I take 18 times 17, see how that will make this number bigger? Divided by 24. For this cell, I take 18 times 7. Oh wait, no, 6 by 7 for this cell. 6 by 7, marginal frequencies for this cell, divided by 24. And for this cell, I take 6 by 17, divided by 24. So do you see how multiplying by the marginal frequencies sort of factors in how big these groups ought to be?
Mm-hmm.
This now is going to be the biggest group. This is going to be the smallest group, because that's what we should see. If gender and where you want to go on vacation have nothing to do with each other. You do a question or you're just stretching. And that's how you would do it. Do you want to work it out?
No.
Once you have these expected frequencies, you would do exactly what you did before to calculate your chi-square. And so if we work this out, let's say we got a chi-square of something small, like 1.67. Let's say that's what we calculated. And the critical value was, I don't know, 3.86. Would you retain or reject the null hypothesis? Retain. You would say self-identified gender has nothing to do, does not influence, does not go with or relate to where you choose to go on vacation. That's exactly sort of what we see here, right? This is the biggest group, as it should be. This is the smallest group, as it should be. That make sense? Yeah? And so what are the degrees of freedom here? Is it categories minus 1? 4 categories minus 1? Yeah, it's columns minus 1 multiplied by rows minus 1. You take the categories of the first variable, gender, 2 minus 1. The categories of the second variable, 2 minus 1. And you multiply those two together to get your degrees of freedom. So degrees of freedom would be 1. Any other concepts from chi-square that are super important? Everyone know my name?
No.
I would know my name.
What's your first name? What's your first name?
Jennifer, it's Jenny.
Oh, duh.
I invited you all to call me on the first day, and then nobody does. Professor Moses.